Hello, everyone. My name is Jay Metz, and I am the chair for the Ultra Ethernet Consortium, also known as UEC. It's a true pleasure to be able to talk briefly about what we're doing and how we're aiming to address the issues that we find affect networks in the age of artificial intelligence. In the brief time together today, I'm going to talk about why the needs of AI, which are far more involved and complicated than the phrase implies, requires a new way of thinking about Ethernet networking. We're going to be talking about how Ultra Ethernet is approaching these problems, and we'll wind up with where to get more information, including blogs, white papers, and even information on how to join if you want to. Now, at this point, there's no shortage of wit and wisdom about how AI is going to change the world. I do happen to believe this for myself, although we have to be careful about whether or not it's for a good way or bad way. But if you do a quick online search for how AI will change networking, and you'll have more answers than you'll have years to read it all. But what about the networking infrastructure is it that you need in order to handle that kind of workload? Well, the obvious answer is bigger, faster, and better. But what does that really mean? I mean, we're talking about incredible amounts of data, data that needs to be moved, data that needs to be processed, data that needs to be converted into usable structures. So there's more to it than just point A to point B. As a matter of fact, with all that data that gets moved around, you're probably very tempted to say, well, just, bigger, faster, better means, thicker pipes. But it's a lot more complicated than that. Once you get beyond the speeds and the feeds, it becomes clear that there's much more to it. Now, the reality is that AI is not just some monolithic thing. It's not so simple as running a math program on a server and feeding it petabytes or exabytes of data. The workloads not only have ever-increasing memory bandwidth and capacity needs, but being able to have that data where and when they're needed is far more complicated than at first glance because of the fact that you have these dependencies about where the data needs to be. It becomes extremely important that you get them where they need to go as quickly as possible. Even better, if you don't have to move the data at all, if you can avoid the I/O, that's the best I/O you can get. Some of these workloads have extended operation times in matters of hours, days, or in some cases, even weeks. So obviously, every single moment that we can use in spending in efficient networks is going to be much better. But before we begin, let's start talking about what we are and are not going to be working on. Okay. So for instance, we're not going to be making a wholesale forklift upgrade for the Ethernet network. Bog standard LAN, WAN, general Ethernet traffic is far outside the scope of the work that we're doing. We're not touching your normal data center Ethernet network. This is specifically for the type of workloads that involve AI and HPC. Because after all, those workloads have specific requirements for GPUs and other accelerators. And that can be broken down into two different types of networks. You can have a scale out network and you can have a scale up network. Now, a scale up network contains things like GPUs that are tightly coupled in pods with shared memory. It involves very high bandwidth, low latency, and low power requirements. All right. Now, a scale out network provides connecting things like that, those pods together to enable very large workloads to go across up to 1 million endpoints. Now, at Ultra Ethernet, we're specifically focusing the scale out network problem at this time. That means that orange link between the different nodes and what's called the backend scale out network on the graph. That's what we're working on right now. We're avoiding getting distracted by focusing on anything else. So the issues at hand are that the processes within the AI workloads, well, they create data relationships that they increase exponentially. So as we add more and more parameters to models, the need for these data points to be sent, it adds major stress on the network, and something of a logarithmic fashion, no less. Well, to add to that complication, different types of workloads have different effects. So for instance, summarization workloads place a burden on computation, whereas generation workloads place a burden on memory. And some of these things work really well with CPUs, and some of them work really well with GPUs, and some of them get really bad performance when you mix and match the processors. So these need to be treated differently inside of the network. Now, both of them, though, spend a great deal of time in the network. So for instance, let's say you've got a work recommendation workload. Right? It's the kind of thing when you go on to an online shopping experience and the site tells you, well, people like you bought this or looked at that or wound up buying that. Well, that kind of functionality, that workload, that spends almost 60% of its time in the network I/O. Now, that means that ultimately the network becomes a huge influence on the net result of the end user's experience, but not just the end user's experience, also inefficiencies in the network can create, well, disastrous effects. Specifically, we want to talk about something called good put. Now, the good put is the ratio of completed work to the total attempts at the work. So for example, anytime you have 2 points that are communicating together and the link is successful and you're sending data from one to the other, that's a good throughput. However, anytime you have a problem or you have to wait for responses, that affects good put, right? The inefficiency of when you get the data to be able to transmit the work to get completed, well, that affects your good put. So needless to say, the more data movement, the more things that are likely to break. And at the very least, it's going to cause a cascading effect of negative impacts inside of that network. So when we start looking at the good put, the speeds and the feeds increase, the scale of the network increases, the chance of errors increase, and all the way from the physical through up to the workload, right? Everything from bit error rates on the wire up to software bugs at the top of the stack. All of these things are affecting, the efficiency of the network. Now, right now, these scale out issues are already put to the limit a few tens of thousands of endpoints. That's where we currently have our limit for the kind of networks that we're talking about. But this isn't a linear impact. It doesn't, we don't just add one problem for every one node we have. It's a logarithmic or exponential increase. By the time you get to 1 million endpoints, there are considerations all up and down the stack. Now, what we have here is an abbreviated list of some of the pain points, but they're all interrelated. They interact with each other, and those inefficiencies compound. And when you start to add in the greater speeds and the greater scale, that makes everything much, much worse. So let's take an example of a particular network workload, network approach to solving this particular problem and how we reach the natural boundary of efficiencies. Let's take a look at the Verbs API. Now, protocols that use the Verbs API ensure in-order packet delivery. Now, there's a very good reason for this because of the fact that you want to be able to ensure that you don't have the very costly reorder effect at the endpoint, right? You don't want to send all the data across the wire to an endpoint where then it has to be set inside of a buffer and then ultimately winds up having to have extra computation to reorder the sequence of the memory data so that it can be put into the proper buffers. So the Verbs API requires that you have in-order packet delivery. Now, in order to do this, the network architects employ a static routing of packets. And if something goes wrong, you've got full message retransmission. So if the packet drops, got to do the whole thing all over again. And that's what's called a go back and recover. You go back a certain number of packets to be able to retransmit them and start all over again. Well, that's inefficient use of the network, right? Every time you have to stop, start over, do it over again, you're not getting your good put that you're looking for. So this becomes a problem when you have multiple stages along the way. And then as a result, that can suffer from head of line blocking and network congestion problems. So the key thing to keep in mind is that the probability of these issues increase with the number of endpoints and interconnections between those endpoints. When these things get inefficient, that winds up propagating the inefficiency over time, and the utilization of the network goes down in terms of the amount of good put. It ties up your network bandwidth, it creates underutilization of available links, and well, quite frankly, your good put is shot to hell. So if in a perfect world, you're going to be able to have all of the links used at all the time. Order is only enforced if the workload really requires it. Things like control messages are important, but sometimes data transmission outside of the control doesn't necessarily need to be in order. So you want to be able to mix and match when necessary without having to force it one way or the other. So where things get truly messy is when you take into consideration the increasing number of dependencies in completed work items. So let's take training, for example. Now, training is highly latency bound because the last bit back is the most sensitive measurement for completion at each stage. And that latency naturally increases when you have a workload that's based upon the number of output tokens, which in turn are affected by the latency introduced by the number of parameters used to deliver those tokens. And here we are talking about very large models that are going from 175 billion parameters in GPT-3 to 1 something trillion in GPT-4, and each of those parameters requires tweaks and moves and relationships between the different endpoints to generate those tokens. Now, what this means is that bigger, better, and faster your network gets, the worse it's going to perform because the errors compound. And that means that when you have these kinds of workloads that require more and more interactions across the board in order to get to each individual and more accurate token, that requires more network functionality, more network efficiency. So obviously the network needs to be tuned to address these issues at these speeds and scale. Well, introducing Ultra Ethernet, UEC. So as you can imagine, this is a big problem, huge, enormous, and one that deserves a concerted effort on the part of the entire tech industry in an open and free sharing of ideas. So for that reason, here we are. Now, as it happens, there is an increase in the use of Ethernet networks for handling the rise of AI and HPC workloads. Well, there's a reason for this. It's an incredibly flexible technology, and that makes it easy to push the limits of what's possible. Now, those limits are very real. And because Ethernet was designed to be a general purpose networking technology, there's still room for improvements for making it more efficient, especially on a workload basis. Now, as far as the organization is concerned, we started last year in 2023, and UEC has become one of the fastest growing projects inside of the Linux Foundation. And as of this recording, it's grown to more than 70 companies in less than 6 months. There's more than 800 individual active contributing volunteers working across 8 work groups. One of the things you'll notice, by the way, is that UEC has built in the tuning characteristics for workload-centric results. Not only are we working on the traditional OSI layered model, but we have intersecting projects that ensure alignment up and down the stack, including critical elements that involve storage, management, performance, and compliance. Now, I've been talking about workload-specific tuning, but what does that mean exactly? Well, put simply, our goal is to handle these workloads at scale, but not all scale-out systems are going to be used the same way. Public cloud needs to use AI and HPC differently than on-site deployments, for instance. So as we were trying to figure out the different profiles for what was necessary for which, it actually wound up being a relatively simple way of describing this, that we've got AI profiles for public cloud, AI profiles for on-site, HPC profiles for public cloud, and HPC profiles for on-site. And it's all built in and integrated into UEC from the start. So now many people are lured in by the sexiness of the speeds and feeds. I confess I'm attracted to a high-end network as much as anybody else is. And we know that the Ethernet speeds are starting to reach the stratosphere, 400, 800, terabit, 2 terabits, million bits of terabits and stuff, and go make you drool. If you're a physical layer geek, or you just like the specs and you like to see the performance numbers of, transporting the entire Encyclopedia Britannica, for those of you who remember what that is, in less than a nanosecond, there's your job, right? But I have to confess, when it comes to the physical layer, the math goes off the charts very quickly. So it's more of I'm a groupie when it comes to this than I am an actual engineer on the physical layer. But the level of precision that we're talking about is truly awe-inspiring. What you do with those speeds, though, is equally as interesting, right? How do you know you're going to be able to do what you say you're going to do when it comes to having a stable, reliable network with 7-figure endpoints? Well, you work your way backwards. That's how. Right? You need to know what's happening in very large networks with extremely tight tolerances, and that means great telemetry. You need to be able to detect and communicate congestion issues end to end, and you need to be able to keep it secure. You need to be able to ensure that the proper data structures and application programming interfaces are supported so that the workloads don't need to be rewritten. Nobody wants to rewrite their programs. Then you need robust transport semantics that work with all of the above. Now, as I said, when you change the perspective a little, shifting from connectivity requirements to workload requirements, you start to see that there's an awful lot of touch points all the way up and down the networking stack. Now, the reason why Ethernet was the basis for this was pretty straightforward. There was no need to reinvent the wheel. As you can see in the graphic, there's an awful lot of the Ethernet layers that are not touched at all. We're able to take that incredibly strong foundation and simply add the tweaks necessary to provide the requirements for each profile. The Ultra Ethernet Transport, or UET, provides for the multipath packet delivery and fine-grained load balancing through packet spraying. Advanced congestion control and telemetry techniques means that this efficiency doesn't get penalized at a greater scale. It also permits the flexibility in the workload requirements for reliable and unreliable traffic flows, as well as in order and out of order delivery, all while still be completely compatible with collectives libraries. So as you can see, the core key elements of Ultra Ethernet is in fact in the transport delivery system, but with additional focuses and tweaks that are optional outside of the transport layer to help augment the entire stack for tuning the workload from the physical layer all the way up into the software layer. So Ultra Ethernet then is looking to accomplish all of these things right from the word go. You see what I mean when I said it's an ambitious project? We start with a philosophical question. What does a reliable, stable, consistent, and predictable system look like at 1,000,000 nodes? What do you need in order to make all of that work? Well, the answer is a lot more involved and a lot more complex than simply trying to find a one-size-fits-all quick fix. You really need to examine all the pieces in the puzzle. So let's take a look at these a little bit deeper. Now, one of the things that we've noticed is that the current methods for providing high-performance networking, like everything else, comes with trade-offs. Now, what we do now, unfortunately, is not the most efficient use in the network because the penalty to the workload is pretty severe if the packets aren't received in order. There are several rigid mechanisms in place to avoid that from happening. Now, what we want to do is use every available path to effectively spray the packets across those paths. This helps us use the network properly as well as reduce tail latency problems. Now, as a matter of fact, this has additional benefits as well. It makes the network workload optimized and even programmable, not to mention adaptable to fluctuating conditions. So this means that we can actually do a kind of a underneath the covers benefit inside the network without having to make application developers panic because they need to make specific changes. Now, it's those fluctuating conditions that happen inside the network that cause most of the problems, right? Network design is often over-designed as a result of that. You usually build out more network than you really need because the congestion and congestion spreading are very real issues and concerns. Some nodes send and receive traffic more often than other nodes, which can lead to asynchronous usage of the network links. It can create things like incast, which is when you have a lot of data coming into a specific node, which creates back pressure inside of the network. All of that increases latency and it increases jitter for the workloads. And some workloads just don't like that kind of jitter. They don't do well with wild variability. Now, that must mean in order to remove the need to have over-engineered networks, you've got to have really robust congestion handling. And that means that you've got to do it from the sender's perspective as well as the receiver's perspective when necessary. But you also need to be able to communicate that across the network in a timely and useful manner. That means improved congestion signaling, appropriate telemetry mechanisms, and so that you know how to deal with those signals, all while ensuring that security is built in from the very beginning. So as we've seen, the UEC approach is an ambitious one, but designed to address not only the current problems in networking that workloads have revealed, but also future-proof for wow, say that 4 times fast, future-proof for even larger and more robust needs moving into the future. Wow, future, how many times do I have to say future? This is a drinking game already. So this means that we've looked at every stage of the Ethernet process in order to be able to improve this. From the traditional method of using required in-order delivery, now we have a much more flexible out-of-order packet delivery with in-order message completion capabilities built into the semantic layer inside of the Ultra Ethernet transport. In regular systems, you've got security that is kind of sometimes seen as an add-on. It's a afterthought. We've got security built in right from the word go directly into the packet formats. Traditional methods have flow-level multipathing, whereas we're taking it from a packet spraying perspective. We can actually transmit packets across multipath environments, not just entire flows. Traditional RDMA-based networking has a number of different congestion notification methodologies, but we are looking at a sender and receiver-based congestion control system that is advanced to handle the very large systems up to 1,000,000 endpoints. The rigid networking that you would normally find in traditional networks has been modified into a semantic level to be able to handle the different profiles as necessary and even allow for certain levels of multi-tenancy for the workloads inside of the network. But most importantly, we're addressing the big elephant in the room, which is what is the scale? Right now, the scale is 10 to low tens of thousands of nodes for simultaneous endpoints, but the goal for Ultra Ethernet is up to 1 million endpoints. So overall, we're trying to approach all of these from the intended consequences of an entire full stack solution for the workloads to be handled. Now, I've only been able to give you a brief update as to what it is that we're trying to do, understand the reasons why we have actually created Ultra Ethernet in the first place, the ambitious nature of the project rather than just trying to tweak one layer or another, or as may be the case, assume that simply because you create a faster network, everything is going to work better. In this particular case, a rising tide doesn't lift all boats if there's more boats in the water. So time prohibits, as I said, prohibits me from going further, but as you can imagine, there's a lot more to go. And if you've got additional questions, I do encourage you to go out to the ultraethernet.org website and take a look at our white paper, which outlines these topics. We've also got blogs that discuss developments towards the 1.0 specification, and there's a lot more. There's also a form where you can sign up to get notified about announcements, membership dates, and so on. So please do rate this session. The feedback you provide will help make future seminars even more valuable. Again, my name is Jay Metz, and it has been a pleasure talking to you today.